Welcome back to Everything About Public Schools. My name is Blaine Helwig. Today's video focus will be on fraction and decimal equivalency, specifically using the decimal point to assist students to easily convert decimals into fractions and vice versa. Pleased to have you join us. This video on fraction and decimal pedagogy is intended for 4th through 6th grade. However, it may be helpful to middle and high school teachers tutoring academically struggling students. There is a free downloadable PDF packet with all the exercises referenced in this video located at the website thenewthree-rseducationconsulting.com under the video tab. Or just Google my name, Blaine Helwig, and follow the links. Let's jump right in. When elementary students are first exposed to decimal numbers, the vast majority of students experience confusion in several ways. First, how big is this number? Second, what does this number physically mean? Third, how does this decimal thingamajig fit into what I already know about whole numbers? Let's look at a common example of a decimal number. 12.046 or 12 46 thousandths. Easy for adults, but a challenge for young students. Why? It's got a lot of digits, 5, and it has a period in the number. The place value appears backward and confusing to students. Instead of ones, tens, hundreds, thousands, from the decimal point to the left, that's normal, it's tenths, hundreds, thousands, and 10,000ths. And there are no oneths. At first glance, the decimal number seems to make no sense. Many students may think, I'm comfortable with whole numbers, but where does this decimal number fit in? All of that student confusion can easily be cleared up with solid pedagogy in the classroom. There is a method that allows students a mental learning crutch, so all students, when initially exposed to decimals, easily compute an equivalency and comprehend a decimal's numeracy elements. Let's examine this method in detail. Back to our decimal, 12.046 or 12 46 thousandths. Let's find an equivalent mixed number to this decimal. I recommend stopping the video and writing this decimal on a sheet of paper and following along as your students would work this exercise. Doing ingrains content for either children or adults. First, write a 1 directly under the decimal point. Second, write a 0 under each digit, including zeros, to the right of the decimal point. Third, add a comma and a horizontal line to simulate the fractional piece of the decimal. Fourth, write the equivalency, the original decimal. This step is very important that teachers press students. It ingrains the understanding of the equivalency process. In short, the decimal, 12.046, is equivalent to the mixed number 12 and 46 thousandths. Final note, the word and is synonymous with the decimal point when reading a decimal auditorially. In contrast, a whole number is not read with an and. For example, 12,046 is read 12,046 as it's written with no and. It is not read 12,046. That is incorrect. But the decimal, 12.046, is read 12 and 46 thousandths. The word and is only used with decimals. Let's discuss the 5 salient points of our decimal work that students should own to mastery via a threshold number of repetition. Let's bring back our decimal and fractional equivalency example and discuss the 5 points for reflective clarity. Number 1, globally, the decimal size or magnitude is solved for students with an equivalent mixed number. More details on this topic in point 5 below. Number 2, the decimal's place value digits to the right of the decimal are now visible to the student. The 0 is in the tens place, since the 0 is over the 10 in the denominator. The 4 is in the hundredths place, since the 4 is over the 100 in the denominator. The 6 is in the thousands place, since the 6 is over the 1,000. But the equivalency process also shows the value of each digit to the right of the decimal point. The decimal's 3 digits to the right of the decimal point indicate the following values: 0 tenths, 4 hundredths, and 6 thousandths. Of course, the overall decimal's value to the right of the decimal point is 46 thousandths. Work as many examples as needed until the process and vocabulary is fluid in your pedagogy, so you are comfortable with the content when you're in front of your students. We'll work 4 more examples in the next couple of slides to practice a little bit more. Number 3, the student knows that their decimal, 12.046, is between 2 whole numbers. It's clear the decimal is between the whole numbers 12 and 13. It is highly recommended that the teachers press this point each time with their students. This exercise solves the mystery of where decimals fit into their whole number schema. since it's clear that a decimal is part of a whole number as shown in an equivalent fraction or mixed number form. Number 4, let's examine the equivalent proper fraction and the mixed number 46 thousandths. Let's take the discussion back to the fundamentals of basic fractions. 46 thousandths means there are 46 boxes shaded out of a total of 1,000. This tells us a lot about the relative size of this decimal number, specifically that the decimal is between two whole numbers, 12 and 13, and that it is closer to one of those two whole numbers than it is to the other. Number 5, continuing from point 4, the teacher is ready to ask their students the following question. Is 46 thousandths closer to 0 or 1 whole? It is apparent that if only 46 boxes are shaded out of 1,000, that the fraction is closest to 0 and not 1. Thus, 12.046 is closer to 12 than it is to 13. It is highly recommended that when beginning to teach decimal number size or magnitude, that teachers provide their students decimal examples that are close to whole numbers. For example, 8.09 and 2.1 on the low side, or 5.98 and 7.84 on the high side. In doing so, students rapidly begin to develop a basic size of the decimal from both a qualitative and quantitative perspective. The related short video, Understanding Decimal Magnitudes, delves into this process much more completely. It considers every decimal number location between any two whole numbers. It also addresses distance calculations between beginning and ending whole numbers, quarter and half points. That video is also available for viewing on the same website listed at the beginning of this video. Let's look at an example with a decimal less than 1 whole, 0.98, and compute an equivalent proper fraction to this decimal. I recommend working the next 4 examples concurrently with me. Stop the video as needed. First, I rewrite my decimal and use the decimal point by placing a 1 directly under it. Add zeros under each digit to the right of the decimal point to create the fraction's denominator. Add a horizontal line to simulate a fraction, and then add in the equal sign. Finally, rewrite the original decimal to complete our equality. And with very little effort, we have calculated our decimal fraction equivalency. Focus your students' attention on the 9 and the 8. The place value of the 9 is in the tens place, and the place value of the 8 is in the hundreds place. Stress to your students that the value of the 8 and the 9 are as follows: 9 tenths and 8 100ths. Press students on the overall decimal value, in this case 98 hundredths. I would make sure that the students know that the numerator is 98 items shaded and the denominator is a total of 100 equal size squares. Finally, the magnitude of the decimal. How big is it? The decimal, 0.98, is between 0 and 1. No whole numbers. But is the decimal closer to 0 or 1? Students should examine that 98 out of 100 shaded is more than 1/2 or 50 over 100. Therefore, the decimal, 0.98, is closer to 1 whole. Students must mentally know the halves of 10, 100, and 1,000. Before moving on to decimals greater than 1 whole, let's compute an equivalent proper fraction of the decimal, 0.402. First, I rewrite my decimal and use the decimal point by placing a 1 directly under it. Add zeros under each digit to the right of the decimal point to create the fraction's denominator. Add a comma and a horizontal line to simulate a fraction, and then add in the equal sign. Finally, rewrite the original decimal to complete our equality. And presto, we've calculated our decimal fraction equivalency. Again, focus your students' attention on all 3 digits, the 4, the 0, and the 2. The 4 is in the tenths place, the 0 is in the hundreds place, and the 2 is in the thousands place. The individual values of the 4, 0, and 2 are as follows: 4 tenths, 0 100ths, and 2 thousandths. Students' ability to view decimal place value and value in this manner is a first step that separates a numerate student from one who is not. Let's look at the overall decimal value. In this case, 402 thousandths. How many equal parts are shaded? 402. Out of the fraction's denominator, 1,000 in this particular case. And finally, a main numeracy factor, the magnitude of the decimal. This step is key to immediately knowing the approximate physical location of the decimal or mentally mapping the decimal on a whole number line. The decimal, 0.402, is between 0 and 1. It has no whole number digits, but is the decimal closer to 0 or 1? Students should examine the 402 out of 1,000 shaded and see that it's less than 1/2 or 500 thousandths. Therefore, the decimal, 0.402, is closer to 0. As is easily seen, students must know with automaticity that the fraction 1/2 is equal to 5 tenths, 50 hundredths, or 500 thousandths. Again, this math area is broken down in its entirety in the associated video, Teaching Decimal Magnitudes Correctly. It's the final stage of the complete student numeracy relating decimals to both proper fractions and mixed numbers. Let's circle back and work two more quick examples and compute equivalent mixed numbers to decimals that are greater than one whole. Our first example is a decimal 7.6. I rewrite my decimal. A quick instructional comment before continuing. It's recommended that teachers specifically question their students at this juncture in their instruction. For example, two possible questions with follow-up may be: 1. Is the decimal equivalent either a mixed number or a proper fraction? How do you know? 2. The decimals between what two whole numbers? Name them. I also recommend drawing a quick number line as a visual, with only whole numbers listed. In this example, 6, 7, 8, and 9. Ask your students to approximate on the number line where they think the decimal number is physically located. If teachers repeat this exercise every day for 3 to 4 days, students will get it. Students only need the repeated practice and guidance so they know what is important and what is not. Again, we use the decimal point. Place a 1 directly under it. Add a 0 under the 6 to the right of the decimal point to create a denominator. Draw your horizontal line to create a separation between the numerator and the denominator. Add in the equal sign and rewrite the original decimal to create the equality. Focus your students' attention on both place value and value. The place value is tenths and its value is 6/10. Of course, the whole number 7 is in the ones place. How many equal parts are shaded? 6 out of a total of 10 equal parts. The fraction is the denominator. The decimal 7.6 is between 7 and 8. However, is the decimal closer to 7 or 8? Students should examine that 6 out of 10 are shaded, which is over 5/10. Therefore, the decimal 7.6 is closer to 8. One last example of finding an equivalent mixed number from a decimal that is greater than one whole. First, I rewrite my decimal. I use the decimal point. Place a 1 directly under it. Add zeros under the 8, 0, and 4. The numbers to the right of the decimal point to create a numerator. Add a comma. Include a horizontal line. Add in the equal sign and rewrite the original decimal to create the equality. Focus your students' attention to both place value and value of the 8, 0, and 4 as we did in the previous 3 examples. Do not forget to include the 10s and 1s for the 27. The overall decimal value was 804 thousandths. How many equal parts are shaded? 804 out of 1,000. The fraction is the denominator. The decimal 27.84 is between 27 and 28. However, is the decimal closer to 27 or 28? Students examine that 804 are shaded out of 1,000. Since 804 thousandths is greater than 500 thousandths, the decimal 27.04 is closer to 28. Now, let's reverse gears and convert a proper fraction to an equivalent decimal. It only requires a bit of reverse engineering and then comparing our answer. If we are given the proper fraction, 81 hundredths, let's find its equivalent decimal. Students should immediately recognize that this fraction, 81 hundredths, is a proper fraction, meaning that it's less than 1. How do we know that? There are no whole numbers. Place an equal sign. Guess. That's correct. Guess a decimal. But it's a highly educated guess from a basis of practice and general knowledge of fractions and decimals. Why? Because students have mastered computing equivalent proper fractions from decimals. So, their initial guess should be very close. Most likely, only one number will be incorrect to the right of the decimal point. Add another equal sign. Rewrite the original decimal and do our little 1 under the decimal point, add zeros, include a horizontal line. In this case, check, since we recreated the original proper fraction, 81 hundredths. If the initial decimal guess was incorrect, such as 0.801, the proper fraction would not match. Then a student guesses again and checks. If this guess and check process is sufficiently practiced, students will understand it and do very well. There is one truism in human learning. Whatever a human being practices to threshold repetitions, they master. Whatever is not practiced, human beings, whether kids or adults, do not know or remember the content. It is that simple. Next, converting a mixed number to an equivalent decimal. Again, a little reverse engineering is required, and we're off to the races. Given the mixed number 4 and 27 thousandths, let's find its equivalent decimal. Students should immediately notice the mixed number. It contains both a whole number and a fraction. The fractional part, a proper fraction, is relatively small. How does the student know this? Well, there are only 27 shaded in the numerator out of a total of 1,000 equal parts in the denominator. Thus, the fraction is relatively close to 0. This basic fractional knowledge should help the student with their initial decimal guess. Place our equal sign, use an educated guess on our decimal number, 4.270. Add another equal sign and rewrite the original decimal. Then use the 1 under the decimal point process to compute an equivalent mixed number and compare our answer against the original mixed number to determine if they match. Nope, our mixed number doesn't match the original. 4 and 27 thousandths is not equal to 4 and 270 thousandths. Hence, let's add in our inequality sign. In summary, since the original mixed number doesn't match, the decimal, 4.270, is incorrect. The student immediately realizes their decimal guess was not correct. So a student may make a second attempt by trying 4.027. Let's continue our discussion with the multiple choice assessment application. Students are often given multiple choice standardized assessments in 4th through 6th grade, where there are 4 answers provided in a decimal or a fraction mixed number format, and they are required to match the answer. For example, Pedro has a string that is 2 and 407 thousandths feet long. Which decimal below is equivalent to his length of string? Simply add a 1 under the decimal point and the correct number of zeros on each of the 4 possible answer choices and match the converted equivalent decimal to the original mixed number in the text of the problem. Now, match which of the 4 possible choices equals 2 and 407 thousandths. Not A, not B, not C. Check. Bubble D. The last 3 topics are important ones. They ensure that students grasp the basic decimal mechanics that greatly improve their mathematics understanding. Topic 1. Many elementary students do not really understand that the decimal point has always been present in whole numbers. It's just been hiding. Write some whole numbers on the whiteboard or the document camera screen. Students should copy these same numbers on a piece of paper at their desks. Let's write some whole numbers. 5, 11, 146, 1. Then ask your students, where are the decimal points located in each of these whole numbers? Let them place the decimal points where they believe the decimal point is located. Then show them that the decimal point is always behind the whole number, even if it's not written. I think teachers will be amazed that so many of their students do not possess this basic knowledge. However, with 3 or 4 days of quick mini lessons and the numeracy gap, if it exists, will be rectified. Topic 2. Adding zeros behind the decimal point while maintaining equivalency. Let's work an example. 9 is equal to 9. Let's place a decimal point behind the second 9. Then we can add zeros. Many students do not grasp that zeros can be added after the decimal point and not change or affect the equality. As before, repeat this exercise each day with a couple of examples until the skill is mastered by all students. Topic 3. We already proved that zeros can be added behind the decimal point of a whole number and not change the overall decimal value when we showed that 9 was equivalent to 9.000, adding zeros to infinity. However, let's look at a more difficult decimal equivalency. 3.7 is equal to 3.7. But let's add a 0. Are the 2 decimals still equal? Is 3.7 equal to 3.70? Let's prove it. Let's rewrite our decimal equivalency. Then convert the decimals to equivalent mixed numbers. Now we have 3 and 7/10 is equal to 3 and 71/100. But we know that 0 over 0 as a fraction is equal to 0. 0 over 0 is equal to 0. So we can add or remove the zeros and we can see the equality is unchanged. So 3.7 is indeed equal to 3.70. Or we can use money to physically show the equivalency is also valid. 7 out of 10 dimes equal to 70 cents, equals 70 out of 100 pennies, which is also equal to 70 cents. If further proof is warranted, have your students use a 100 grid. Have students shade 7/10. Then, using the same grid, have students shade 70 over 100. They will discover that 7/10 and 70 100ths are equivalent. They occupy the same area. Therefore, 3.7 is also equal to 3.70. A quick recap of the video. 3 main points and 1 recommendation. Point 1. Place a 1 directly under the decimal point and add zeros under each digit to the right of the decimal point. This allows students to A. Understand place value and value of each digit to the right of the decimal point, tenths, hundreds, thousands, etc. And B. Create equivalent fractions from a decimal number of any size. Point 2. Reverse engineer a proper fraction or mixed number to compute an equivalent decimal. Then check that decimal to make sure it's correct. Point 3. Use the 1 under the decimal point to locate the correct response on multiple choice tests. And prove that a 0 can be added to the right of the decimal, leaving the overall value of the decimal unchanged. And a recommendation. Teachers, please provide threshold repetitions so students may master the content. Thank you for watching. I hope this short video is helpful in your work in the public schools. Please check out our other videos and resources.